In first semester, we have done, sir, Engineering Mathematics 1. In second semester, Engineering Mathematics 2. In third semester, sir, we have done Linear Algebra, Real Analysis, Operational Research, Scientific Computing, and Probability and Statistics. In fourth semester, sir, we have done Differential Equation, Complex Analysis, and Abstract Algebra, Nonlinear Optimization, sir.
Mhm. Mhm. So, yeah, so okay, so I am little bit. So how we are going to because you have stochastic calculus. So for that, so for example, in your syllabus you have Ito calculus, Ito integral, all those things. So
Actually, we don't know familiar with stochastic terms, sir. We have studied calculus in our college.
exactly, that's the thing. That's why I am little bit confused that how to introduce the because you are not familiar with the stochastic process and all, right?
Yes, sir.
So the stochastic calculus itself will be little bit. I mean, it will be difficult for me also and for you also to take you. I mean, uh,
Sir, one thing we will can do, sir, first read the basic lectures from calculus to stochastic calculus, how we can shift. After that, we will follow our syllabus.
no, look, there are as you did in the probability, there are discrete part and there are continuous part. Okay, so
Yes, sir.
discrete part you do the discrete time and for continuous part you do continuous random variable. So stochastic calculus or this ethos calculus, this everything is some sort of continuous in time. Similarly, stochastic process also has discrete time stochastic process and continuous time stochastic process. So my concern is if you don't have the discrete time stochastic process itself, then doing the continuous time because your syllabus is in continuous time. So, but your but you don't have the basic this. You did not study the discrete time stochastic process. So that's why I'm little bit confused how to manage the things. So anyway, we can start because as you did discrete random variable, continuous random variable, similarly, you need something of uh, discrete time stochastic process and continuous time stochastic process. Okay. So we can, yeah, I think we should focus on discrete time for the time being and then see how much we can do because directly going to the continuous it does not make sense much and also continuous time you need certain concept of measure theory. Do you have measure theory in upcoming semester sometime?
The major theory, I think it is not there in our coming semester.
That's the problem. So uh, uh, yeah. And yeah, all of you, if you wish, you can switch on your video. I mean, there is nothing wrong in that. I mean, if you wish, you don't have to. It's your choice, whatever you want. Uh, so Okay, we'll start with discrete time this thing, and we'll see what we can do. Probably I'll follow this textbook, whatever is there, the first one, I'll follow that. Okay. So this textbook you have uh, yeah, understand so this first, so you Brezhniak and Zastwani, we'll follow that. Okay.
Yes, and please share the PDF also.
Yeah, I will. You don't have the PDF?
No, sir.
You can download. I will. I'll write. In a list.
Okay, it is free, sir.
Sorry.
It is free on internet.
Yes, yes, yes.
Okay, sir.
I don't know. I mean, you can just download somewhere. So we'll do Monday 2 classes and Wednesday, Thursday 1 class. Okay. Yeah. So let me join from. Am I audible?
Yes, sir.
Hope you can see my screen, right?
Yes, sir.
Let us start. I mean, if there is if you cannot see, or just let me know if you have any problem and see.
It is fine, sir.
Mhm. Okay. So we'll start from the beginning. Okay. So first it's is is we'll start with sigma field. Okay. Is the definition of sigma field. So what is a sigma field? It's let omega be a non-empty set. So a sigma field on over this omega is a family of subset of capital Omega such that one, so it satisfies certain properties. Like first property that so 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 mm, so sigma field you can denote it by like if, okay. So it's a notation. Suppose the sigma field F over omega is a family of subsets of omega such that uh, I mean, many places you can have an empty set. Okay? So the empty set, so this is the empty set or null set, whatever you said. Empty set. This belongs to capital. And sorry, just a mistake. The sigma field, or in many books you will find capital omega is in it. Okay, so either empty set in S or complement. This is the complement. So either empty set will be in F or the capital omega will be in F. Okay, and number two, if A belongs to F, then then A complement will belong. So if A belongs to F, then A complement will also belongs to F. Okay. Point number three is if A1, A2, A3. So this is a sequence of sets, okay, is in F. Then their countable union, so union n equal to 1 to infinity an will also belongs to. So first definition is sigma field. So in the probability lecture, did you did this thing? Did you did sigma field definition?
No, sir.
No. Okay. Okay. So yeah. So the definition. So definition of sigma field is like that. That if you have omega is a non-empty set. Okay. A sigma field over F, a sigma field F over omega is a family of subsets. Okay? So what is a sigma field? It is collection or family of subsets. Okay, it's a family of subsets over omega, and which satisfies So the sigma field, so any collection of subsets over capital omega should satisfy these three properties. The null set or the whole set will be in F. If any set is in F, their complement should be in F. This is script F. If AI is the sequence of this A1, A2, A3 is in F, then their countable union will be in F. Okay. So if AI is in F, then their countable union will also. So we can work with some examples. Suppose the another important point in this third point is this countable union. Okay. So if A1, A2, A3 is in F, then their countable union will also be in F. It is not saying that the finite union, okay? It's not saying the finite union. It's just saying that it's a countable union. Okay. So, for example, what is the example of countable set? Is natural number set is countable? Is it countable?
No.
Anyone can answer. Please, you can open your mic, open your screen. Nothing. No problem. Okay. So, is natural number is countable set?
No, sir.
Huh?
No, sir.
Why?
Also, we cannot count all the element of that set, sir. The number of element in that natural number is infinite, sir.
Yes, that's okay. That infinite. So there are different concepts. One is countable, then you have uncountable, then there is finite, and then there is infinite, right? Now, what is the countable and uncountable? What is the difference? Whatever you can count, correct? Count means you have a
Yes.
biject.
Yes.
Like 1, 2, 3, 4, 6, 7, 8. It could be infinity. How does it matter? But you can count, right? You can continue to count. It is not finite. That's fine. Infinite, but you can count, right? This is the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th. There is no issue in counting, right? So finite set means that you have a finite number of things like A, B, C, right? This is also countable and finite. But the natural number set where you have these things, that is like 1, 2, 3, dot, anything. So this is also you can count first, second, third, and fourth, fifth, but infinite. Infinite. There is no point in counting. For example, what about the rational number set? So the set of rational number. The set of rational numbers. What about the set of rational number? Is it countable or uncountable?
Uncountable.
Why?
Yes, sir, we cannot count like 1, 2, 3, sir. In two natural number, between two natural numbers, there are infinite rational number also, sir.
You see, so what is the set Q? So how you can write it is the like m by n, right? These are the rational numbers. Okay. Correct. These are rational numbers. Sorry. I just have a mistake. Mn belongs to n or z. So what is the difference between z and n?
Sir, n have only positive integers
Yes.
without zeros, sir.
And z has positive, negative both, right?
Yes, sir.
And you can consider zero with you can some places it is n union zero, then zero is included, and anyway z has zero, so it's a plus minus, so it's a positive, negative integers. Okay. Now set of rational numbers is like what is this 4 by 5? This is rational. What is this? Is this rational number?
Yes, sir.
Yes. So this is also an example of rational number, right? So Q is the set of rational numbers m by n, and Mn belongs to Z. I mean, you can say it is belongs to Z. I mean, that's better. Yes. Belongs to Z. Look, the rational number set is also countable. So why it is countable? What is the proof that this anything is 4 by 5 or anything is countable? Look, you can write.
We can find one-to-one mapping.
Sorry. Repeat.
There is a one-to-one correspondence in the set.
Yes, there will be one-to-one correspondence with the natural numbers. So, for example, you can write 1 by 1, 1 by 2, 1 by 3, 1 by 4, dot, 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 dot. Okay. The first row. Then you write 2 by 1, 2 by 2, 2 by 3, 2 by 4, dot, dot, dot. Then you can write 3 by 1, 3 by 2, 3. And similarly, you can write 4 by 1, 4 by 2, 4 by 3, 4 by 4. And similarly, you can continue this. Once you do it, now you see you have, so like you do it like this. Okay, so what you observe in this diagonal, if you just consider this diagonally, so what is the what is the sum of numerator and denominator? In the first one, it is 2, right? In the first diagonal, it is 2. In the second one, here the numerator denominator sum is 3, correct? Right? Hello?
Yes, sir.
And similarly, in the third, this diagonal, so it is 3 by 1, 2 by 2, and 1 by 3. You see there some numerator plus denominator, it is 4. So in the first diagonal, it is 2, then second diagonal 3, this is 4, and in the third diagonal, it is 5, right? And similarly, in this diagonal, it will come as 6, and as well as this will come as 7, and as you see, this will give you something like 8. So in a sense that you do the numerator plus denominator and you get the you are getting almost all the natural numbers, right? Correct? right?
Yes, sir.
And any rational number m by n, it will appear in such present representation throughout the thing, right? Correct? It will appear in such representation, and this sum. So in each diagonal, this thing. So you have 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's basically you are getting the natural number correspondence again, and each row. Sorry, each diagonal. You see here is a 1 element, here is a 2 element, here is a 3 element, here is a 4 element, and the sum is 5. So and another thing is, suppose you have two countable set. So union of two countable set is again countable. Union of two countable set is again countable. Right? So you have, it's not about, I'm not talking about finite. Finite is of course countable. Union of two countable set is also countable, right? So suppose you have a natural number set which is n, which is infinite. It's countable, but infinite, right? And suppose you have another set, I call is A, and this set contains two numbers, 1 and 7. Okay. Now, what is A union N? Anybody?
And sir.
N. So it is A union N is N, right? So this is N is countable, correct?
Yes, sir.
So if you have two countable sets, their union is again countable, correct? So it does not matter whether it is finite or infinite. So you have a finite set which you take union with the n. This is n. So similarly, suppose you take z union n. What it will be? What?
Right.
It will be z. So here you are taking z is countable, n is countable. So both are countable, and their union is also countable, right? But both in this countable. So here you see so all in each diagonal wise, if you see the each diagonal wise, each diagonal there are countable elements, right? Each diagonal there are countable elements. So their union is also again countable, correct? This is the proof of that Q is rational number set is also countable, because each diagonal is countable. Their union will also again be countable. As a result, the rational number set is also countable. Okay? Infinite, fine, but countable. Don't make confused with the countable and infinite thing. It can be infinite set, fine, but it's a countable thing. So countable means you have a bijection with the natural number set. That means you can assign for every set element, you can assign one each number. For example, here I assigned 1, 2, 3, 4, 5, 6, 7, 8 in this way, right? So I can assign a natural number set with this Q. As a result, Q is, so it's a bijection. Any set which is a bijection with the natural number set is called countable set. Okay. It is not that it is finite, infinite, anything. I mean, It's okay. Finite is okay. Finite is easy. Infinite it may be, but it's a countable thing. Okay. So Z is countable, N is countable, Q is countable. What about R? The set of real numbers. What about
It is also countable.
also countable? No, the
Uncountable.
it's uncountable because what is R? So what you have in R, what is there? So one thing you have noticed that a natural number set can be written as a subset of Z, right? Correct? Is it fine, this statement? Is it correct or wrong?
Yes, sir, correct.
It is correct, right? Natural number is a subset of Z. And yeah, and what about Q? So, for example, Q is the set of rational numbers, and what is by definition is M by N, such that M N belongs to Z. Correct? Right? This is my definition of Q. This is my definition of Q. Now, now this is, if this is the definition of Q, then so any natural number or any rational any Z, can I? So for example, you take any like 4, right? So 4 I can write it always as 4 by 1, right? Correct. This will also be in Q. So for example, -5, you can always write it as -5 by 1. So this is always on Q. Okay. So because you can express it by M by N, and in the lowest this integer form, that's okay. So in a sense that you can have N, Z, and Q. Correct? Is it true?
Yes, sir.
This inclusion, is it true?
Yes, sir.
Yeah. So I have natural number set, I have real Z integer set, I have rational numbers set. Okay. And what is here? What is in R? What is here?
Well, it is subset of complex number.
No. So complex, you forget, man. You must tell me what is the relation between R and Q.
Q is subset of R.
Q is a subset of R. Why?
Well, real number is a combination of rational and irrational number.
So you have real number is a combination of rational. So you have rational plus irrational. Correct? So what is the definition of irrational number?
Which number we cannot represent as a rational number?
Yes.
Like in P by Q form.
Yeah. So you cannot write it as P by Q form. That's correct. Okay. So any example of uh, any example do you know for irrational numbers?
Root 2.
Yeah. So you can have you have suppose EI is there, pi is there, and then whatever it is root 2, whatever we are saying is fine. I mean root 2 is there. Okay. So 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 in a sense that so in a sense that you have rational number and irrational number. So what we have proved that rational or discussed with the rational number is a countable, right? But irrational numbers are uncountable. The rational number set is countable, where irrational number is uncountable. Because the point is you cannot have that one-to-one bijection because you cannot write it in P by Q form, correct? As a result, you cannot have that one-to-one bijection in there. That's why the irrational numbers are the set of irrational numbers is uncountable because you cannot have a one-to-one bijection with the natural numbers. So if you have countable and uncountable, their union is always uncountable, right? Because you have a countable thing and uncountable thing, their union is always uncountable. Okay. So so in a sense that so this is countable, Z is countable, Q is countable, but R is uncountable. Okay. So R is uncountable. But you see, all of them are infinite sets. So finite, infinite, the concept is different. Finite means you have a finite number of things. Infinite means you are infinite. But you have a infinite sets which are countable. And even so even you have
Is there any finite set which is uncountable?
finite set.
Which is uncountable?
No, finite set means you have finite number of elements, right? Like you have A1, A2, AN. Correct? So, okay. Suppose I take a set, I consider a set of E. Suppose I consider a set E equal to E pi root 2. So is this set countable or uncountable? A. Is this set countable or uncountable? A. Anyone? I have considered a set which has three elements, E, pi, and root 2. So is this set countable or uncountable?
What is the 1-1 mapping, sir? Here, I am thinking for that 1-1 mapping.
Ah,
I am not getting any function to map directly to all natural numbers.
Sorry.
But for countable set definition is that set is there is one mapping with natural number. Then
Correct.
its set is countable, sir. Then I am thinking that mapping which maps this set to natural number. If that mapping is 1 1.
Yeah.
If there is any mapping, then that set is countable. If there is not any mapping, then that set is not countable.
Correct. So what about this A set? Yeah, so A is countable. Though the set, each of the element of the set is irrational numbers, but A has only 3 elements, right? A has only 3 elements.
Yes, sir.
Each element is irrational number. Each element of the set is an irrational number. That's a separate issue. But whether the set A is countable or not, the set A is countable because it has only 3 elements. So with any natural, so this is the first element, this is the second element, this is the third element, right? The set A is countable because it has only 3 elements. The set of irrational numbers is uncountable, right? Set of rationals is countable. And so the question was whether there is any finite set which is uncountable. No, the finite set means it's finite, right? Finite set means it's a finite. You have a finite number of elements. So therefore, that cannot be uncountable. Correct?
Okay, sir, understood.
Huh?
Okay, sir, understood.
Yeah. Yeah, okay. We'll so you have the next class from 11, I think. So your classes are 50 minutes, right? Hello?
Yes, sir. You can take till 1 hour also.
No, 10 to 10:50, I think. So 11, I think there will be some other class. So yeah, so we'll discuss again on Monday.
Okay, sir.
Okay, we'll discuss again on Monday. Okay, thank you.
Okay. Where we will get this notes, sir?
There is no notes, man.
Yes.
I don't have any notes. So I will write here. And while writing, you can just, so there is only definition sigma field I have written, right? So you can have it. While I am writing, you just take, you write whatever you like to write. You don't write whatever you don't like to write. I don't have any notes, okay?
Okay, sir.
I'll teach whatever will come to my mind.